Welcome, friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's first oceans, those ancient waters that emerged from fire and steam nearly 4 billion years ago. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who have already joined along, thank you. The Earth breathes water vapor into a copper sky 4 billion years ago. The planet's surface glows like the inside of a forge, molten rock flowing in slow rivers across a world that knows no solid ground. Temperature readings would melt any thermometer 1200 degrees Celsius at the surface, hot enough to turn stone into liquid honey. But even in this furnace, something patient stirs. Water, locked within the minerals that form the planet, begins its first great escape. Each degree of cooling releases more molecules into the thickening atmosphere, a planetary exhale that has lasted for millions of years without pause. The vapor rises in columns that dwarf any earthly storm, pillars of steam reaching towards space before condensing in the upper atmosphere. These towers of moisture stretch hundreds of miles upward, carrying with them the chemical signature of Earth's interior traces of sulfur, carbon, and metals that will one day settle into the first ocean floors. No rivers exist yet, no lakes, no seas, only this endless breathing of moisture from stone to sky and back again. The water molecules themselves carry stories from the birth of the solar system, forged in the hearts of ancient stars and delivered here through cosmic patience spanning billions of years. Scientists still debate exactly how much water emerged from Earth's interior versus arriving from space. A gentle mystery that lingers in every drop of rain that falls today. Some estimates suggest that half of Earth's water originated within the planet itself, trapped in hydrated minerals during the original accretion process. The other half arrived later, delivered by comets and asteroids over hundreds of millions of years. What remains certain is this unhurried process of release, the planet slowly discovering its capacity to hold oceans within its gravitational embrace. The temperature hovers perpetually near the boiling point of water, creating a world wrapped in mist so thick that the surface remains invisible from space. This early atmosphere, dense with water vapor, carbon dioxide, and nitrogen, creates a greenhouse effect more intense than anything Venus experiences today. The atmospheric pressure builds to nearly 100 times greater than modern Earth, pressing down on the molten surface like a heavy blanket of steam and gas. Only took 40 million years for the surface to cool enough for the first droplets to remain liquid for more than a few seconds. During these early millennia, any water that managed to condense immediately flashed back to vapor upon touching the glowing ground. The planet existed in a state of perpetual near boiling, neither fully molten nor capable of supporting liquid water for any meaningful duration. This delicate balance between steam and liquid played out across the entire globe. A planetary-scale chemistry experiment with no observers save the stars themselves. The early atmosphere, thick with carbon dioxide and nitrogen, creates this greenhouse effect that keeps the world warm even as the young sun burns 25% dimmer than today. This faint young sun paradox puzzled astronomers for decades. How could early Earth remain warm enough for liquid water under such a dim star? The answer lies partly in this dense atmospheric blanket, trapping heat with an efficiency that modern Earth's thin atmosphere cannot match. Water vapor swirls in currents that follow no familiar weather patterns, driven by heat rising from every square mile of molten surface. Convection cells the size of continents carry moisture upward, where it cools and begins its slow descent back toward the furnace below. These circulation patterns dwarf modern hurricanes, rotating slowly across hemispheres in movements that take months to complete full cycles. The entire planet participates in this atmospheric dance, every molecule of water vapor following currents that spiral from equator to poles and back again, like a planetary sauna. Earth steams in its own primordial warmth. The distinction between atmosphere and surface blurs in zones where superheated vapor meets cooling rock, creating regions of perpetual mist that exist neither as gas nor liquid but something in between. These transition zones shift constantly as the planet's surface temperature fluctuates by mere degrees, enough to determine whether water finds temporary refuge or returns immediately to the sky. The first hints of what will become the water cycle establish themselves during this era. Vapor rising, cooling, condensing, then vaporizing again before ever reaching solid ground. These molecules drift in patient loops, waiting for their moment to fall and stay fallen. Some water droplets manage brief existences of seconds or minutes before the heat reclaims them. But each failed attempt builds toward the moment when surface temperatures will drop just enough for liquid water to persist. The sky holds all of Earth's future oceans in suspension, a vast reservoir floating between space and stone. Every molecule that will one day fill the Pacific, Atlantic, and Indian Oceans drifts overhead, waiting for the planet's fever to break. This atmospheric ocean contains roughly the same volume of water that covers Earth today, 1.37 billion cubic kilometers, but distributed as vapor across a sky so thick that no sunlight penetrates to illuminate the glowing surface below. Crystalline structures begin forming in the upper atmosphere where temperatures drop low enough for water to freeze, creating the first ice in Earth's history. These microscopic crystals drift for brief moments before melting in the warmer layers below, but their existence marks a milestone, the first solid water in a solar system where ice had previously formed only in the cold reaches beyond Mars. The dance between these three phases of water-solid, liquid, and gas begins its 4 billion year performance across Earth's stage. Only took the patience of geological time for this system to find its balance, for the planet to discover that sweet spot between too hot and too cold where oceans could begin their long residence. The molecules wait with the unhurried persistence of stone, ready for their moment to fall from the copper sky and begin the long work of carving Earth's surface into the blue marble that will one day harbour life. The sky opens and begins to weep. After eons of holding Earth's future oceans in suspension, the atmosphere finally releases its burden in the longest rainfall in planetary history. Droplets form in the cooling upper reaches where temperatures have dropped just enough for condensation, each one a microscopic sphere carrying the promise of seas. The first drops descend through layers of superheated air, many evaporating and reforming dozens of times before completing their journey to the surface below. This is not the gentle spring rain that will one day nourish forests, nor the sudden summer storms that will refresh parched grasslands. This is precipitation on a geological scale, measured not in inches per hour but in centuries of continuous downpour. The rain falls without pause for millennia, driven by the simple physics of a cooling planet finally crossing the threshold where liquid water can survive contact with solid ground. Each raindrop represents a victory of temperature over time, of planetary patience over cosmic fire. The atmospheric pressure during this epoch reaches nearly 100 times modern levels, creating conditions where water behaves in ways no human has ever witnessed. Raindrops grow to extraordinary sizes in the dense air, some reaching nearly an inch in diameter before gravity pulls them earthward. These massive droplets fall through the thick atmosphere like liquid meteors, their passage creating sonic booms that echo across the barren landscape. The sound of this primordial rain would deafen any listener, a constant roar of water meeting stone that continues day and night without respite. Scientists estimate this great rainfall lasted anywhere from 10,000 to several million years, depending on local conditions and the planet's uneven cooling rate. The uncertainty arises from the absence of any surviving rock formations. From this period, the geological record begins later, after the heaviest bombardment had ceased and the first stable crustal formations could preserve their stories in stone. This gap in Earth's autobiography leaves the duration of the Great Rain as one of geology's gentle mysteries, a question written in vapour rather than rock. The young sun, still burning 25% dimmer than its modern intensity, provides just enough energy to power this vast atmospheric engine. Solar radiation heats the ocean of vapour surrounding Earth, creating convection currents that lift moisture high into the thickening clouds. These early clouds bear no resemblance to the wispy formations that drift across today's blue skies. Instead, they form continuous layers dozens of miles thick, blanketing the entire planet in a grey shroud that blocks all direct sunlight from reaching the surface. Only took several 100,000 years for the first puddles to appear and actually survive longer than a few minutes. The earliest successful raindrops strike the cooling basalt flows that cover most of Earth's surface, creating tiny pools that steam and hiss but do not immediately boil away. These first collections of liquid water, perhaps no larger than a person could cup in their hands, represent a milestone as significant as the first breath of oxygen that will emerge billions of years later. Lightning illuminates this perpetual storm from within, creating a continuous display of electrical activity that makes modern thunderstorms seem like gentle flickers. The dense atmosphere and abundant moisture provide ideal conditions for massive electrical discharges, some spanning hundreds of miles and lasting for minutes rather than milliseconds. These lightning bolts carry enough energy to split water molecules and forge the first complex chemicals that will eventually participate in life's origin story. The chemical composition of this primordial rain differs significantly from modern precipitation. These early droplets dissolve carbon dioxide, ammonia, and methane from the thick atmosphere, creating a mildly acidic solution that begins the slow work of chemical weathering. Each raindrop becomes a tiny laboratory where atmospheric gases mix with water vapour, forming simple compounds that will later concentrate in the growing pools and puddles scattered across Earth's surface. Temperature variations across the planet create different rainfall patterns in different regions. Areas directly above still active volcanic zones receive superheated steam that condenses and falls as near boiling rain, while regions farther from geological activity experience cooler precipitation that can actually survive contact with the ground. This geographic variation in rainfall temperature creates the first climate zones in Earth's history, establishing patterns that will evolve but never completely disappear over the next 4 billion years. The rainfall rate during peak periods reaches levels that would cause catastrophic flooding on modern Earth estimates, suggest daily accumulations measured in feet rather than inches. However, most of this water immediately runs off the smooth basalt surfaces or pools in temporary lakes that last only until the next volcanic eruption, or landslide fills them with debris. The planet's surface lacks the complex topography that would later allow water to accumulate in stable basins, so most rainfall simply flows toward the lowest elevations and collects in temporary reservoirs. Like a planetary baptism, this endless rain washes Earth clean of its birth debris and begins the slow process of creating the conditions necessary for stable oceans. The water carries away dust from ancient impacts, dissolved gases from volcanic outgassing, and microscopic particles of metal and stone that have drifted in the atmosphere since the planet's formation. Each raindrop serves as both cleaner and catalyst, preparing the surface for the more complex chemistry that will follow once permanent bodies of water can establish themselves. The atmospheric circulation patterns during this epoch follow simple rules. Hot air rises from the volcanic surface, cools as it ascends, releases its moisture as rain, then descends as drier air to begin the cycle again. These enormous convection cells operate on timescales of months or years, slowly redistributing heat and moisture across the planet's surface. The entire atmospheric system functions like a massive heat engine, powered by the temperature difference between the molten surface and the cold of space above. Only took the patience of stone and the persistence of vapour for this system to gradually transform Earth from a molten hellscape into a world where liquid water could finally find purchase. The rain continues its methodical work, each drop a small victory in the long campaign to cool the planet enough for oceans to begin their residence. Above, the clouds gradually thin as the atmosphere releases its burden of moisture. Below, the first permanent puddles begin their quiet existence, waiting to grow into seas. The first puddles gather in basalt cradles, pooling quietly where volcanic stone has cooled into shallow depressions. These earliest collections of liquid water find refuge in the natural bowls carved by cooling lava flows, where molten rock once contracted and cracked as it surrendered its heat to space. Each small basin represents a victory of geometry over temperature, a place where Earth's surface dips just enough to trap the precious droplets falling from the endless grey sky above. These primordial pools measure no larger than a modern swimming pool, perhaps 50 feet across at their widest points. Yet within their modest boundaries lies the entire future history of Earth's oceans. Every molecule of water that will one day fill the Mariana Trench or lap against the shores of continents not yet born. The water sits perfectly still in these volcanic cradles, its surface broken only by the continuous patter of rain, adding drop by drop to the slowly growing reservoirs. The basalt beneath these first pools tells its own story of planetary cooling. This iron-rich volcanic rock, dark grey and fine-grained, formed when the earliest lava flows spread across Earth's surface and cooled rapidly in the thin atmosphere. Basalt makes an ideal foundation for water collection. Its dense mineral structure resists erosion, while its natural tendency to form columnar joints creates the perfect geometry for catching and holding rainfall. The rock's composition also begins the first chapter in ocean chemistry, slowly leaching minerals into the water above. Scientists studying modern basalt formations observe that these rocks weather predictably when exposed to liquid water, releasing calcium, magnesium, and iron ions at rates that can be measured in laboratory experiments. Extrapolating backward through geological time suggests that Earth's first pools quickly developed their own chemical signatures as the surrounding stone gradually dissolved into solution. This process, still occurring today wherever basalt meets seawater, represents one of the planet's most enduring chemical cycles. The temperature of these early pools hovers just below the boiling point of water, creating conditions unlike anything found on modern Earth. Steam rises continuously from their surfaces, but slowly enough that the pools actually grow rather than shrink as incoming rainfall exceeds evaporation losses. The warmth comes not only from the still cooling volcanic rock below, but also from the greenhouse effect of the thick atmosphere above, which traps heat like a heavy blanket wrapped around the entire planet. Only took a few thousand years for the first pools to develop their own microenvironments, tiny ecosystems of chemistry where dissolved minerals began interacting in increasingly complex ways. Iron from the basalt substrate combines with sulfur compounds outgassed from nearby volcanic vents, creating the first precipitates that settle to the bottom of these warm pools. These early chemical reactions proceed slowly in the oxygen-free environment, following pathways that will become impossible once the atmosphere changes composition billions of years later. The pools exist in perfect isolation from each other, separated by ridges of cooling basalt and the irregular topography of the early planetary surface. Each basin develops its own chemical personality based on the specific composition of its surrounding rock and the particular mix of atmospheric gases that dissolve into its waters. Some pools become rich in dissolved carbon dioxide, creating weakly acidic conditions that accelerate the weathering of their basalt containers. Others accumulate ammonia and methane, setting the stage for more exotic chemistry. Lightning from the perpetual storms above strikes these pools with surprising frequency, the water's conductive properties making it an attractive target for electrical discharge. Each lightning strike delivers enormous quantities of energy directly into the warm water, temporarily raising the temperature and driving rapid chemical reactions between dissolved compounds. These electrical events create the first organized energy inputs into Earth's early chemical systems, providing the activation energy needed for molecules to combine in new and unexpected ways. The water in these volcanic basins remains crystal clear despite the constant influx of dissolved minerals. The high temperature prevents most particles from remaining in suspension, While the lack of biological activity means no algae or bacteria cloud the transparent liquid, looking into one of these ancient pools would reveal the basalt bottom in perfect detail, every crack and bubble in the volcanic glass visible through the warm, mineral-rich water above. Evaporation from the pools creates localized weather patterns as water vapor rises and immediately condenses in the cooler air just above the surface. This creates tiny rain systems that operate on scales of mere feet, water evaporating from one end of a pool and falling as fresh rain on the other end, establishing circulation patterns that will eventually evolve into the global water cycle. These miniature weather systems represent Earth's first experiments with local climate, proving that the basic principles of evaporation and condensation can operate at any scale. Like nature's first laboratories, these basalt-cradled pools begin the slow work of discovering which chemical combinations are stable and which quickly break apart in the warm, mineral-rich environment. Simple compounds form and dissolve in endless cycles, each iteration exploring new possibilities for molecular organization. The pools serve as both mixing vessels and reaction chambers, places where Earth's early chemistry can experiment with complexity in the patient, unhurried way that geological time allows. The surrounding landscape shows no signs of life, no hint of the biological complexity that will eventually transform these pools into something unrecognizably different. Instead, the scene displays only the stark beauty of cooling stone and warming water, of rain falling into volcanic basins under a grey sky that has not yet learned the colour blue. The pools wait with mineral patience for the next chapter in their story, content to serve as Earth's first attempts at holding the sky's gift of liquid water. Only took the geometry of cooling stone and the persistence of falling rain to create these first sanctuaries where water could finally rest. The basalt cradles hold their precious contents without complaint, slowly contributing their mineral essence to the growing pools while providing stable foundations for Earth's earliest experiments with ocean chemistry. Above them, the endless rain continues, adding volume drop by drop to reservoirs that will one day overflow their volcanic boundaries and begin the long journey toward becoming seas. Comets whisper their icy gift across the silence of space, approaching Earth with velocities that dwarf any earthly motion. These frozen messengers from the outer solar system carry within their cores the water that formed in the cold reaches beyond Neptune's orbit, where temperatures remain low enough for ice to accumulate grain by grain over millions of years. Each comet represents a time capsule from the solar system's birth, preserving water molecules that have remained frozen for 4.5 billion years, waiting for their moment to join Earth's growing collection of liquid seas. The late heavy bombardment continues its patient work during this epoch, delivering not the catastrophic impacts that scarred the moon's surface, but gentler collisions that add their icy cargo to Earth's water budget without destroying what has already accumulated. These smaller comets, perhaps a few hundred meters across, strike the planet's surface at velocities of 20 to 40 kilometers per second. The kinetic energy of their arrival vaporizes the ice instantly, but in the dense atmosphere that surrounds early Earth, this vapor quickly condenses and falls as additional rain to join the pools already gathering in their basalt cradles. Scientists estimate that cometary impacts during this period could have delivered between 10 and 50% of Earth's total water inventory. Though the exact proportion remains one of geology's enduring mysteries, the isotopic composition of modern seawater provides clues deuterium ratios in Earth's oceans match those found in certain types of comets more closely than others, suggesting that specific populations of these icy visitors contributed disproportionately to our planet's water budget. The chemical fingerprints left by ancient impacts continue to circulate in today's oceans, invisible signatures of cosmic delivery written in the language of atomic mass. The comets themselves originate in two distinct regions of the solar system, the Kuiper belt beyond Neptune and the more distant Oort cloud that surrounds the entire solar family like a spherical shell of frozen debris. Kuiper belt objects follow relatively predictable orbits and arrive with consistent compositions. while Oort cloud visitors travel much more eccentric paths and carry water ice formed under different conditions. This diversity in source regions means that Earth receives a complex mixture of water types, each delivery adding its own chemical signature to the growing atmospheric reservoir. Only took a few million years for the cumulative effect of these gentle impacts to become significant, adding perhaps several centimeters of water equivalent across Earth's entire surface. While individual comet strikes might contribute only modest amounts to the global water budget, the sheer number of impacts during the late heavy bombardment ensures that cometary water becomes a substantial component of Earth's early oceans. The process operates with astronomical patience, dozens of impacts per century, each one adding its small gift to the planetary total. The arrival of each comet creates spectacular displays in Earth's thick atmosphere. Though no eyes exist yet to witness these cosmic fireworks, the icy nucleus begins sublimating while still hundreds of kilometers above the surface, creating a brilliant coma of water vapor and dust that glows in the dim sunlight. This vapor trail stretches for thousands of kilometers behind the comet's path, gradually dispersing into the existing atmospheric moisture and becoming indistinguishable from water that originated within Earth itself. Impact craters from the largest cometary visitors punctuate Earth's surface, but these depressions quickly fill with water from the ongoing rainfall and become some of the first lakes in planetary history. These impact-formed basins, ranging from a few kilometers to several dozen kilometers across, provide much larger collection areas than the small pools forming in natural volcanic depressions. The water that accumulates in these crater lakes carries dissolved minerals leached from the shocked rock created during impact, adding new chemical complexity to Earth's growing inventory of aqueous environments. The orbital mechanics that deliver these comets to Earth follow the same gravitational laws that will eventually stabilize the solar system into its current configuration. Jupiter's massive influence deflects many comets from the outer solar system inward toward the inner planets, where they can encounter Earth during its formative period. This gravitational herding effect ensures that cometary impacts continue at elevated rates for hundreds of millions of years, providing a steady supply of additional water long after the initial planetary accretion process has ended. Temperature differences across Earth's surface determine whether cometary water additions result in immediate vapor, liquid pools, or temporary ice deposits. Comets striking the hottest regions near active volcanic zones contribute their water directly to the atmospheric reservoir, while those impacting slightly cooler areas can create temporary lakes that persist for thousands of years before evaporating. The rare impacts occurring at the poles might even create small ice deposits, though these would quickly sublimate in the warm global climate that characterizes this early epoch. Like cosmic gardeners tending a planetary greenhouse, the comets continue their deliveries with methodical precision. Each impact represents another small step in Earth's transition from a dry, rocky planet to a water world capable of supporting the complex chemistry that will eventually lead to life. The process operates on timescales that dwarf human comprehension, millions of years of patient accumulation, impact by impact, molecule by molecule. The water delivered by these ancient impacts carries with it traces of organic compounds formed in the cold chemistry of the outer solar system. Simple molecules like formaldehyde, methanol, and hydrogen cyanide arrive frozen within the cometary ice, adding to the growing inventory of carbon-based compounds that will later participate in life's origin story. These organic hitchhikers represent some of the first complex chemistry to reach Earth's surface, seeding the planet with molecular building blocks that formed in the darkness between the stars. Modern measurements of noble gas ratios in Earth's atmosphere preserve evidence of this ancient cometary bombardment, showing that significant quantities of xenon and other rare gases arrived via impact rather than through the planet's initial formation process. These atmospheric signatures serve as forensic evidence for the cosmic delivery system that helped fill Earth's early ocean basins, written in isotope ratios that persist unchanged after 4 billion years of geological processing. Only took the patience of orbital mechanics and the persistence of gravitational attraction for these icy messengers to complete their appointed task. The comets continue arriving throughout this epoch, each one adding its contribution to Earth's water budget while gradually depleting the reservoir of frozen material in the outer solar system. Their gifts accumulate in the growing pools and lakes scattered across the planet's surface, patient additions to the liquid inventory that will one day become the cradle of all earthly life. Salt dissolves from newborn rock with the unhurried persistence of geological time, seasoning the growing pools with Earth's first chemistry. The basalt that cradles these early waters contains within its crystalline structure the mineral essence of the planet's formation iron, magnesium, calcium, and sodium locked within volcanic glass that formed when molten rock met the cooling touch of atmosphere. Each molecule of water that contacts this stone begins a gentle conversation, a chemical dialogue that will continue for billions of years, as oceans slowly extract the dissolved minerals that give seawater its distinctive taste and composition. The process begins at the molecular level, where water molecules surround individual ions within the basalt's crystal lattice and gradually coax them into solution. Sodium and chloride ions, the primary components of modern table salt, emerge first from the weathering volcanic rock. These ions require relatively little energy to separate from their mineral hosts, making them among the earliest additions to Earth's chemical inventory. The warm temperature of these primordial pools accelerates the dissolution process, allowing mineral extraction to proceed hundreds of times faster than it would in cooler water. Calcium follows sodium into solution, leached from the feldspar crystals embedded throughout the basalt matrix. This dissolved calcium will eventually precipitate as limestone and other carbonate minerals, but during these early epochs it simply accumulates in the warm water, gradually increasing the pool's mineral content with each passing millennium. The calcium ions bond readily with dissolved carbon dioxide from the atmosphere, forming the first bicarbonate compounds that will later become crucial components of ocean chemistry and biological processes. Scientists studying modern basalt weathering observe that fresh volcanic glass dissolves approximately 10,000 times faster than the same material after it has developed a protective surface layer through exposure to water. This means that Earth's earliest pools, in contact with freshly cooled volcanic rock, experienced rapid mineral accumulation that gradually slowed as protective rinds formed on the exposed basalt surfaces. The chemical evolution of these pools therefore follows a predictable pattern: rapid initial enrichment followed by slower, steady mineral accumulation over geological time. The iron content of these early waters exceeds anything found in modern oceans by factors of thousands. Iron readily dissolves from basalt in the oxygen-free environment that characterizes early Earth, creating pools with a distinctive greenish tint that reflects the abundance of dissolved iron ions. This iron-rich water would appear toxic to any modern life forms, but during this epoch it simply represents the natural chemical signature of a planet, still in the process of differentiating its surface composition from its interior. Only took several 100,000 years for the mineral content of these pools to reach concentrations that would be considered brine by modern standards. The combination of rapid basalt weathering and significant water evaporation in the warm climate creates conditions where dissolved salts can accumulate to levels approaching saturation. Some pools develop mineral crusts around their edges, where evaporation concentrates the dissolved ions beyond their solubility limits, creating Earth's first natural salt deposits. Magnesium emerges from the weathering basalt in quantities that rival sodium and calcium, contributing to the complex ionic balance that characterizes these early brines. Modern seawater contains magnesium in precisely the ratios needed to support biological processes, but these ancient pools develop magnesium concentrations based purely on the mineral composition of their volcanic containers. The resulting chemistry creates conditions unlike anything found in nature today, establishing baseline compositions that will evolve over billions of years toward the familiar chemistry of modern oceans. The pH of these mineral-rich pools shifts gradually toward alkalinity, as dissolved ions interact with carbon dioxide from the atmosphere. The weathering of basalt naturally produces alkaline conditions, buffering the acidic effects of dissolved atmospheric gases and creating chemical environments where complex mineral precipitation can begin. This pH buffering represents one of Earth's first examples of chemical homeostasis, a self-regulating system that maintains relatively stable conditions despite ongoing inputs and outputs. Trace elements begin appearing in solution as the weathering process extracts not only the major mineral components, but also the small quantities of rare metals distributed throughout the basalt matrix. Copper, zinc, manganese, and nickel dissolve in parts per million concentrations, creating the first solutions containing the metal cofactors that will later become essential components of biological enzymes. These trace metals accumulate slowly but persistently, establishing chemical inventories that will prove crucial for the eventual emergence of life, like planetary blood. These mineral-rich waters carry the chemical essence of Earth's interior toward its surface, redistributing elements that formed during the planet's accretion into new configurations that can participate in surface chemistry. The dissolved ions remain in constant motion through thermal currents and evaporation-driven circulation, ensuring thorough mixing of the chemical constituents within each pool. This circulation prevents the formation of chemically stratified layers and maintains uniform mineral concentrations throughout the water column. Precipitation events begin occurring as mineral concentrations approach saturation limits in the warmest, most concentrated pools. Calcium carbonate forms the first mineral crusts, depositing as thin white films on the basalt surfaces where water levels fluctuate due to evaporation. These carbonate deposits represent Earth's first sedimentary rocks, chemical precipitates that record the mineral composition of the early atmosphere-ocean system in crystalline form that can survive geological processing. The salinity of these early pools varies dramatically based on local conditions, with some remaining relatively fresh, while others develop brine concentrations that exceed modern seawater by factors of 10 or more. This chemical diversity creates a natural laboratory where different types of mineral precipitation and chemical interaction can occur simultaneously across the planet's surface. Each pool becomes a unique experiment in early ocean chemistry, exploring different pathways toward chemical complexity. Sulfur compounds begin appearing as hydrogen sulfide gas from volcanic emissions, dissolves into the warm waters and oxidizes to form sulfate ions. These sulfate additions create entirely new chemical possibilities, including the precipitation of calcium sulfate and other evaporate minerals that form when the pools become sufficiently concentrated through evaporation. The sulfur chemistry adds another layer of complexity to the growing inventory of dissolved constituents that characterize these early aqueous environments. Only took the patient interaction of water and stone to establish Earth's first chemical ocean, a distributed system of mineral-rich pools that collectively represent the planet's initial experiment with aqueous geochemistry. The dissolved salts accumulate grain by grain, ion by ion, creating the chemical foundation that will eventually support all marine life. The process continues without haste, following the thermodynamic laws that govern a mineral's solubility and chemical equilibrium, gradually building toward the complex chemistry that characterizes modern seawater through the simple expedient of dissolving stone. Steam rises, falls, rises again in Earth's first rehearsal of the water cycle that will one day orchestrate weather across continents and oceans. Above the growing pools and temporary lakes, invisible columns of water vapor ascend through the dense atmosphere, carrying heat from the warm surface toward the cooler heights where condensation waits to reverse their upward journey. This vertical dance of molecules represents the planet's discovery of convection, the fundamental process that will eventually distribute energy and moisture across the globe with the precision of a cosmic clockwork mechanism. The evaporation occurs continuously from every exposed water surface, accelerated by temperatures that hover just below the boiling point and atmospheric pressures that create unusual thermodynamic conditions. Water molecules escape their liquid bonds and rise as individual vapor units, each one carrying a tiny portion of the thermal energy stored in the pools below. The process proceeds molecule by molecule, an imperceptible exodus that gradually transfers entire lakes into the atmosphere over timescales measured in centuries rather than seasons. Condensation nuclei in the early atmosphere consist primarily of volcanic dust, salt crystals from evaporated pools, and microscopic particles of cosmic debris from the ongoing bombardment. These tiny solid specks provide surfaces where water vapor can transition back to liquid form, creating droplets that grow through collision and coalescence until gravity overcomes atmospheric buoyancy. The abundant condensation nuclei ensure that water vapor rarely remains gaseous for long periods, creating conditions where the atmosphere operates near saturation with respect to water. Scientists studying atmospheric physics recognize that Earth's early water cycle operated under fundamentally different conditions than those governing modern weather systems. The dense atmosphere and uniform global temperatures eliminated many of the pressure gradients that drive contemporary storms, creating instead a more gentle, persistent circulation pattern. Convection cells formed and dissipated slowly, operating on timescales of months or years rather than the days or weeks that characterize today's weather phenomena. The absence of large continental masses means that this early water cycle operates primarily over volcanic terrain, with no significant temperature differences between land and sea, to drive the complex circulation patterns that characterize modern climate systems. Heat distribution occurs through simple vertical convection, rather than the horizontal transport of energy that occurs when warm ocean currents encounter cold continental interiors. This simplified geography creates correspondingly simplified atmospheric dynamics. Only took a few million years for this primitive water cycle to establish regular patterns of evaporation and precipitation that began reshaping Earth's surface topography through the patient work of erosion and deposition. Water flowing from elevated volcanic features carved the first channels in cooling basalt, creating drainage networks that concentrated rainfall runoff into ever larger temporary streams and rivers. These early waterways lasted only as long as individual rain events, but left permanent scars in the landscape that guided future water flow along predictable paths. The vertical extent of this early water cycle reached extraordinary heights due to the thick atmosphere and strong convection currents driven by high surface temperatures. Water vapor ascended to altitudes of 50 kilometers or more before encountering conditions cold enough to force condensation, creating cloud systems that dwarfed any formations seen in modern skies. These towering cumulus structures contained water equivalent to entire modern river systems, cycling moisture between surface and atmosphere on scales that beg a contemporary comparison. Residence times for water molecules in the atmospheric portion of this cycle averaged several months, compared to the 9-day average that characterizes modern atmospheric moisture. The dense air and strong convection patterns kept water vapor aloft for extended periods, allowing individual molecules to travel vast distances before returning to liquid form. Some molecules completed several vertical circuits between surface and high atmosphere before finally condensing and falling as rain, creating a thoroughly mixed atmospheric reservoir that homogenized chemical compositions across the planet. Temperature variations with altitude in the early atmosphere followed different patterns than those observed today, primarily due to the greenhouse effects of water vapor and carbon dioxide concentrations that exceeded modern levels by factors of hundreds. The atmospheric temperature profile remained relatively warm even at great heights, preventing the formation of ice crystals that characterize high-altitude clouds in contemporary weather systems. All precipitation fell as liquid water, regardless of altitude or season, like a planetary engine driven by solar energy and volcanic heat. This early water cycle began the work of redistributing thermal energy across Earth's surface. Hot regions gradually cooled as evaporation carried heat upward and away, while cooler areas warmed slightly as condensation released the latent heat of vaporization. The process operated slowly but inexorably, smoothing temperature extremes and creating more uniform conditions that favored the accumulation of stable water bodies. Humidity levels throughout the lower atmosphere remained near 100% saturation due to the abundance of surface water and the warm temperatures that promoted rapid evaporation. This created conditions where fog and mist persisted continuously, reducing visibility to mere hundreds of meters and creating an perpetually overcast world shrouded in its own water vapor. The distinction between cloudy and clear skies had no meaning during this epoch, as atmospheric moisture levels remained too high to permit transparent air. The chemical composition of precipitation evolved gradually as the water cycle began incorporating dissolved atmospheric gases into the rain that fell on surface pools and lakes. Carbon dioxide, ammonia, and sulfur compounds dissolved readily into the condensing droplets, creating weakly acidic rainfall that enhanced the weathering of exposed rock surfaces. This chemical feedback loop accelerated the dissolution of minerals from basalt and other volcanic rocks, increasing the salinity of surface waters and establishing the first connections between atmospheric chemistry and ocean composition. Circulation patterns within individual pools and lakes developed in response to the continuous addition of fresh precipitation and the loss of water through evaporation from their surfaces. Thermal convection created mixing currents that prevented chemical stratification and maintained uniform temperatures throughout the water column. These internal circulation systems ensured that minerals dissolved from the bottom sediments remained well mixed with incoming rainwater, preventing the development of chemically distinct layers. Only took the simple physics of phase transitions and density differences to establish this fundamental planetary process that will continue operating for the next 4 billion years with increasing sophistication and complexity. The early water cycle represents Earth's first experiment with global circulation systems, proving that the basic principles of evaporation, condensation, and precipitation can create stable, self-regulating patterns of moisture distribution. Steam continues rising from the growing pools, condensing in the grey clouds above, and returning as rain that feeds the same pools that provided the original vapour, creating an endless circulation that connects sky and surface in Earth's first functional weather system. Shallow seas spread across continents that exist only as collections of volcanic islands, water finding its level with the patient determination of gravity itself. As the pools and crater lakes gradually overflow their basalt boundaries, streams of warm water begin connecting isolated basins into larger networks of interconnected waterways. These first rivers flow not through valleys carved by ancient glaciers or erosion, but across the relatively flat volcanic plains that comprise most of Earth's early surface topography. The water moves slowly, following subtle gradients measured in inches per mile rather than the dramatic slopes that will characterize mountain-fed rivers in later geological epochs. The continental masses of this early Earth bear no resemblance to the familiar shapes of modern geography. Instead of the 7 distinct continents that will eventually emerge through billions of years of tectonic activity, the planet's solid surface consists primarily of scattered volcanic archipelagos separated by vast expanses of cooling basalt plains. These proto-continents rise only a few hundred feet above the surrounding terrain, creating minimal topographic relief and allowing shallow seas to spread across enormous areas with depths measured in meters rather than kilometers. The absence of significant mountain ranges means that water accumulation occurs primarily through the simple process of filling topographic depressions, rather than through the complex drainage patterns that characterize modern continental watersheds. Rainfall collects in every available low spot, creating thousands of temporary lakes that persist until the evaporation or overflow connects them to larger bodies of water. This creates a constantly changing mosaic of wet and dry areas as water levels fluctuate in response to local rainfall patterns and evaporation rates. Scientists studying paleogeography estimate that these early shallow seas covered approximately 60% of Earth's surface, compared to the 71% coverage of modern oceans. However, the distribution pattern differed dramatically from today's configuration, with water spread across numerous small basins rather than concentrated in a few large ocean basins. The average depth of these early seas rarely exceeded 50 meters, creating vast expanses of warm, sunlit water that remained well mixed throughout their entire depth. The temperature uniformity across these shallow seas created conditions unlike any marine environment that exists today, without deep ocean basins to isolate cold bottom water from warm surface layers. The entire global ocean system maintained relatively constant temperatures of 40 to 50 degrees Celsius. This thermal homogeneity eliminated the temperature-driven circulation patterns that characterize modern oceans, creating instead a more static water mass that moved primarily in response to atmospheric pressure differences and tidal forces. Only took several million years for these expanding water bodies to begin exhibiting the chemical stratification that occurs when evaporation concentrates dissolved minerals in isolated basins. Some shallow seas became increasingly saline as water loss exceeded inputs from rainfall and runoff, while others maintained relatively fresh compositions due to continuous dilution from atmospheric precipitation. This chemical diversity created the first examples of different marine environments, each with distinct mineral compositions and physical properties. Wave action in these shallow seas operated on scales completely different from modern ocean waves. The limited fetch available across small basins meant that wind-generated waves rarely exceeded heights of a few meters, creating gentle surf conditions along the volcanic shorelines. However, the warm water temperatures and high mineral concentrations created unusual wave dynamics, with surface tension effects that produced smaller, more closely spaced wave patterns than those observed in contemporary oceans. Tidal effects began manifesting as these growing water bodies developed sufficient size to respond noticeably to lunar gravitational forces. The Moon, orbiting much closer to Earth during this early epoch, generated tides with amplitudes that dwarfed modern tidal ranges. These extreme tides, with vertical ranges exceeding 20 meters, created vast intertidal zones where water alternately flooded and exposed broad expanses of volcanic terrain twice each day. These tidal flats became Earth's first examples of regularly cyclic environmental conditions, establishing rhythms that would eventually influence biological evolution. The chemistry of these expanding seas reflected their volcanic origins, with dissolved iron concentrations that gave the water a distinctive greenish hue, and mineral compositions that would prove toxic to most modern marine life. Iron, magnesium, and sulfur compounds dominated the chemical signature of these early oceans, creating reducing conditions where chemical reactions proceeded along pathways impossible in today's oxygen-rich environment. These unique chemical conditions established the geochemical foundation for processes that would later become crucial to life's emergence. Like liquid mirrors reflecting the grey sky above, these shallow seas created Earth's first large-scale aquatic ecosystems. Though they remained completely sterile of biological activity, the warm, mineral-rich waters provided ideal conditions for complex inorganic chemistry, with dissolved compounds interacting in combinations that would become impossible once oxygen began accumulating in the atmosphere. These chemical interactions proceeded slowly and methodically, exploring pathways toward molecular complexity that operated purely through thermodynamic principles. Sediment accumulation in these early seas occurred primarily through chemical precipitation, rather than the biological processes that dominate modern marine sedimentation. Calcium carbonate, silica, and iron compounds crystallized directly from the supersaturated waters, settling to the bottom in layers that recorded the changing chemical composition of the overlying water. These chemical sediments created Earth's first marine rock formations, preserving records of ocean chemistry that can still be deciphered in the geological formations that survived subsequent tectonic processing. Circulation patterns within these shallow seas developed primarily through thermal convection and tidal mixing, rather than the complex current systems driven by temperature and salinity gradients that characterize deep oceans. The uniform depth and temperature eliminated most of the density differences that drive modern ocean circulation, creating relatively static water masses that moved slowly in response to atmospheric pressure systems and the gravitational effects of solar and lunar tides. Seasonal variations had minimal impact on these early seas due to Earth's different axial tilt and the moderating effect of the dense atmosphere that smoothed temperature extremes between day and night or between different latitudes. The oceans experienced only gradual changes in temperature and chemistry, over timescales measured in thousands of years, rather than the seasonal cycles that punctuate modern marine environments. This temporal stability allowed chemical processes to proceed without the interruptions that characterize contemporary ocean chemistry. Only took the inexorable force of gravity and the patient accumulation of rainfall to transform Earth's scattered pools into the first true marine environments. The shallow seas continue expanding as volcanic activity creates new basins and ongoing precipitation adds to their volume. Water spreads across the cooling planet with liquid determination, finding every depression and filling it to the brim before overflowing toward the next available basin, gradually connecting isolated chemical laboratories into the first global ocean system that will eventually nurture life itself. Tides begin their eternal dance as the young moon pulls at these new waters with gravitational forces that dwarf any modern tidal influence. The moon, orbiting perhaps 20,000 kilometers closer to Earth than its current distance, exerts tidal forces nearly 50 times stronger than contemporary lunar effects. These primordial tides rise and fall with amplitudes that reach 20 to 30 meters, transforming vast expanses of shallow seafloor into temporary landscapes that alternate between underwater plains and exposed mudflats with the reliable rhythm of celestial mechanics. The gravitational choreography operates with mathematical precision even in this early epoch, following the same inverse square law that will govern tidal forces throughout Earth's future history. As the moon traces its elliptical path around the planet, the varying distance creates spring and neap tidal cycles with extreme ranges during lunar perigee and more modest fluctuations when the moon reaches its farthest orbital point. These cyclical variations establish Earth's first predictable environmental rhythms, creating conditions that change dramatically twice each day with clockwork regularity. The tidal bulge that follows the moon's passage stretches across hundreds of kilometers of shallow sea, creating moving hills of water that travel at speeds approaching 50 kilometers per hour. The wavefront of an incoming tide resembles a wall of water advancing across the flat volcanic plains, flooding areas the size of modern states within a matter of hours before reversing direction and exposing the same terrain to air and starlight. This creates the largest regularly moving feature on Earth's surface, dwarfing even the massive convection cells that drive atmospheric circulation. Scientists studying tidal mechanics recognize that these early extreme tides dissipated enormous amounts of energy through friction with the shallow sea floor, gradually slowing Earth's rotation and simultaneously forcing the moon into progressively higher orbits. The planet's day during this epoch lasted perhaps 18 hours rather than the 24-hour period that characterizes modern Earth. The rapid rotation combined with extreme tidal forces created complex interference patterns where tidal waves from different directions met and either reinforced or cancelled each other. The physical effects of these massive tides transformed the early sea floor through processes that have no modern equivalent. The repeated loading and unloading of 20-meter water columns created pressure changes sufficient to fracture bedrock and drive hydrothermal circulation through crustal rocks. Each tidal cycle pumped enormous volumes of mineral-rich water through cracks and pores in the volcanic substrate, accelerating chemical weathering and establishing circulation patterns that connected surface and subsurface water systems. Only took a few thousand tidal cycles for these extreme water movements to begin carving permanent channels in the soft sediments accumulating in tidal zones. The rushing water of incoming tides scoured deep grooves in mud and sand, while the retreating flow deposited sediments in complex patterns that recorded the direction and strength of tidal currents. These early tidal channels created the first organized drainage networks on Earth's surface, establishing pathways that guided water flow long after individual tidal events had passed. The intertidal zones created by these extreme tides encompassed areas larger than modern continents, vast expanses of temporarily exposed sea floor where unique chemical and physical processes could occur. During low tide, these areas experienced direct exposure to the atmosphere, allowing chemical reactions between marine sediments and atmospheric gases that were impossible in permanently submerged environments. The alternating wet and dry conditions created ideal laboratories for exploring the boundary conditions between aquatic and terrestrial chemistry. Temperature variations in the tidal zones followed patterns unlike any modern environmental conditions. The thermal mass of 20-meter tidal ranges meant that water temperatures changed slowly despite the dramatic twice-daily exposure to atmospheric conditions. Tidal pools left behind by retreating waters maintained elevated temperatures for hours, creating warm chemical reactors where dissolved minerals could precipitate and redissolve in response to changing conditions. These thermal effects added another layer of complexity to the already rich chemistry of the early oceans. Sediment transport by these powerful tides operated on scales that transformed entire regions with each tidal cycle. The enormous water volumes moving at high velocities could suspend and transport particles ranging from fine clays to boulder-sized rocks, creating constantly changing depositional patterns across the tidal flats. Incoming tides brought marine sediments onto previously dry land, while outgoing flows carried terrestrial materials into the deeper parts of the shallow seas, thoroughly mixing the chemical signatures of different environments, like a cosmic metronome. The Moon's gravitational influence established Earth's first experience with large-scale periodic phenomena, proving that celestial mechanics could create predictable environmental rhythms even in the chaotic conditions of the early planet. The tidal forces operated with astronomical precision, creating conditions that changed dramatically but reliably according to the Moon's orbital position and phase. This predictability represented a stark contrast to the more random variations in volcanic activity and atmospheric conditions that characterized other aspects of early Earth's environment. The sound of these massive tides would have created the planet's first acoustic environment, as billions of tons of water rushed across continental shelves and exposed sea floors with each tidal change. The roar of advancing and retreating water could be heard across hundreds of kilometers, creating a constant background noise that rose and fell with tidal rhythms. This acoustic signature represented Earth's first regular, planet-wide sound. A tidal symphony that played twice daily without interruption for hundreds of millions of years. Current patterns generated by these extreme tides created the first organized circulation systems in Earth's shallow seas, establishing flow patterns that distributed heat, dissolved chemicals, and suspended particles across vast areas. The tidal currents achieved velocities that exceeded any modern oceanic flows, creating turbulent mixing conditions that prevented chemical stratification and maintained uniform compositions throughout the water column. These circulation patterns ensured that materials dissolved from the seafloor became thoroughly distributed throughout the entire ocean system. Coastal erosion proceeded at rates that would reshape entire continents within geological short periods. As the repeated impact of 20-meter tidal ranges gradually wore away even the hardest volcanic rocks, the constant alternation between hydraulic pressure from incoming tides and gravitational drainage during tidal retreat created stress cycles that fractured bedrock and accelerated mechanical weathering. These erosional processes contributed additional dissolved minerals to the ocean chemistry, while simultaneously creating new topographic features that influenced future tidal patterns. Only took the patient influence of lunar gravity and the fluid responsiveness of Earth's growing seas to establish this fundamental rhythm that will continue shaping planetary environments for the next 4 billion years. The tides dance their gravitational ballet with cosmic precision, moving vast volumes of water according to mathematical laws that connect Earth's surface to the orbital mechanics of the solar system. The Moon pulls, the oceans respond, and twice each day the planet experiences its first taste of predictable, cyclical, environmental change driven by forces that operate far beyond the Earth's own internal systems. Hydrothermal vents warm the depths of these shallow seas, releasing Earth's internal heat through underwater springs that create the first warm sanctuaries beneath the cooling surface. Along the fractures where tidal stresses have cracked the volcanic sea floor, superheated water emerges from the planet's interior, carrying dissolved minerals and gases that have been circulating through underground reservoirs for thousands of years. These vents represent Earth's first attempt at connecting its molten interior with the growing ocean system, establishing chemical and thermal bridges between the planet's deep heat and its surface waters. The temperature of water emerging from these early hydrothermal systems reaches 200 to 300 degrees Celsius, hot enough to dissolve minerals that remain insoluble under normal oceanic conditions. Iron, copper, zinc, and sulfur compounds leach from the heated rock at rates thousands of times faster than typical weathering processes, creating mineral-rich plumes that spread through the surrounding seawater like underwater rivers of dissolved stone. These chemical fountains add entirely new components to ocean chemistry, introducing elements that will later become essential cofactors for biological enzymes. The geological setting of these early vents differs dramatically from the deep ocean hydrothermal systems that characterize modern seafloor spreading centers. Instead of forming along organized mid-ocean ridges, these ancient vents emerge wherever tidal stresses and thermal gradients combine to fracture the thin volcanic crust that covers most of the seafloor. This creates a distributed network of venting sites scattered randomly across the shallow ocean basins, each one operating independently according to local geological conditions. Scientists studying hydrothermal chemistry recognize that these early vent systems operated under fundamentally different conditions than their modern counterparts. The shallow water depths eliminated the extreme pressure conditions that characterize deep ocean vents, allowing dissolved gases to escape more readily and preventing the formation of some mineral phases that require high-pressure environments. However, the reduced pressure also permitted chemical reactions that cannot occur in the crushing depths of contemporary hydrothermal fields. The circulation patterns around individual vents create the first examples of localized ecosystems on Earth, though these remain entirely chemical rather than biological. Hot, mineral-rich water rises from the vent orifices and mixes with the cooler seawater above, creating thermal gradients that span hundreds of degrees within distances of mere meters. These temperature differences drive convection patterns that establish distinct chemical zones around each vent, where different minerals precipitate as the cooling water reaches their respective solubility limits. Only took a few centuries for mineral deposits to begin accumulating around the most active vent sites, creating the first hydrothermal mineral formations on Earth's surface. Iron sulfides, silicates, and carbonate compounds precipitate from the cooling vent waters, building chimney structures that can reach heights of tens of meters. These early hydrothermal chimneys grow slowly but persistently, adding new mineral layers with each thermal pulse from the underlying magma chambers that drive the circulation systems. The chemical gradients surrounding these vents establish conditions where complex inorganic chemistry can explore pathways toward increasing molecular organization. Temperature variations create zones where different types of chemical reactions proceed at optimal rates, effectively creating natural laboratories where simple compounds can combine into more complex structures through purely thermodynamic processes. The energy gradients provided by the venting systems represent Earth's first examples of organized energy sources that can drive chemical work. Dissolved hydrogen sulfide from the vents reacts with iron in the seawater to create distinctive black and yellow precipitates that color the water around active vent sites. These sulfide minerals form some of Earth's first colored chemical signatures, creating underwater landscapes painted in metallic hues that stand in stark contrast to the uniformly grey basaltic plains that characterize most of the early sea floor. The mineral precipitates settle in distinctive patterns that record the flow directions and chemical compositions of the ancient vent waters. Gas emissions from hydrothermal vents contribute significantly to the atmospheric composition during this epoch, adding hydrogen sulfide, carbon dioxide, and hydrogen gas to the already complex mixture of gases surrounding early Earth. These emissions create localized atmospheric anomalies where the chemistry differs significantly from the global average, establishing the first examples of regional variations in atmospheric composition. The gas plumes from underwater vents can be detected in the overlying atmosphere for hundreds of kilometers downwind. Like underwater geysers, These hydrothermal systems operate on irregular cycles determined by the thermal dynamics of their underground water circulation systems. Pressure build-ups in subsurface chambers create periodic bursts of high-temperature venting, followed by quieter periods, when circulation patterns readjust to changing thermal conditions. These cycles establish some of Earth's first examples of episodic environmental phenomena, creating conditions that change dramatically over timescales ranging from hours to years. The heating effects of these vents extend far beyond their immediate vicinity, creating warm water masses that influence regional ocean temperatures across areas spanning hundreds of square kilometers. The continuous input of thermal energy prevents local cooling and creates temperature anomalies that persist for thousands of years. These warm zones become refugia where chemical processes requiring elevated temperatures can continue operating even as the global climate gradually cools. Trace element chemistry in the vicinity of hydrothermal vents achieves concentrations that will never again be equaled in Earth's ocean history. Rare metals like gold, platinum, and uranium dissolve readily in the high-temperature vent waters and accumulate to levels thousands of times higher than their normal oceanic concentrations. These extreme enrichments create unique chemical environments where unusual mineral faces can crystallize, and complex metallic compounds can form through processes that require both high temperatures and unusual chemical compositions. The fluid dynamics of hydrothermal circulation create mixing patterns that transport deep crustal materials to the ocean's surface, establishing chemical connections between Earth's interior and exterior that will continue operating throughout planetary history. The vent systems serve as conduits for deep Earth chemistry, allowing materials that formed under high pressure, high temperature conditions to participate in surface chemical processes. This creates feedback loops where surface conditions influence subsurface processes and vice versa. Mineral zoning around active vents creates the first examples of organized spatial chemistry on Earth, with different compounds precipitating at characteristic distances from the heat sources according to their individual temperature and concentration requirements. Copper sulfides form closest to the vent orifices, followed by iron sulfides at intermediate distances, and finally silicate minerals in the cooler peripheral zones. These zoning patterns establish templates for chemical organization that will later be exploited by biological systems, only took the steady heat flow from Earth's interior and the circulation patterns driven by thermal gradients to create these underwater oases where chemistry could experiment with complexity under ideal conditions. The hydrothermal vents continue their patient work of connecting planetary interior to surface, pumping mineral-rich water from the depths, and creating warm sanctuaries where the most sophisticated chemical processes of early Earth can proceed uninterrupted by the cooling temperatures that characterize most of the ocean surface. Chemistry stirs in quiet currents as simple molecules begin their slow dance of combination and dissolution in the patient waters of Earth's first seas. Within the mineral-rich brines that fill the shallow basins and tidal pools, carbon, nitrogen, and sulfur compounds drift in solution, occasionally encountering each other under conditions that favor chemical bonding rather than the random collisions that characterize most molecular interactions. These early experiments in complexity proceed without haste, guided only by thermodynamic principles and the statistical probability that some molecular encounters will produce stable products that resist immediate decomposition. The concentration of organic precursor molecules in these ancient waters exceeds anything found in modern oceans by factors of thousands. Formaldehyde, hydrogen cyanide, and ammonia arrive continuously from atmospheric chemistry and cometry impacts, accumulating in the warm pools where evaporation concentrates their solutions to levels approaching the threshold for spontaneous polymerization reactions. These simple molecules represent the basic building blocks from which all complex organic chemistry must eventually emerge, the molecular alphabet from which Earth will eventually spell the language of life. Catalytic surfaces provided by the abundant mineral precipitates accelerate chemical reactions that would proceed impossibly slowly in pure water solutions. Iron sulfide crystals, silicate minerals, and clay particles created by hydrothermal processes provide organized arrangements of atoms where simple molecules can align in configurations that favor bond formation. These mineral catalysts operate through purely physical mechanisms, offering reactive sites where molecular building blocks can assemble into more complex structures without requiring the sophisticated enzyme systems that drive modern biochemistry. Scientists studying prebiotic chemistry recognize that the conditions prevailing in Earth's early oceans provided ideal laboratories for exploring the transition from simple, inorganic molecules to complex organic polymers. The combination of elevated temperatures, high concentrations of reactive precursors, and abundant catalytic surfaces created environments where chemical evolution could proceed through pathways that remained theoretically possible but practically impossible under modern oceanic conditions. The early seas served as planetary-scale reaction vessels where chemistry could experiment with complexity. The pH gradients established by different rates of mineral weathering create zones within individual pools where acid-base chemistry can drive reactions that would not occur under uniform conditions. Some areas develop acidic conditions as dissolved carbon dioxide forms carbonic acid, while other regions become alkaline through the weathering of basic volcanic minerals. These chemical gradients provide the driving forces needed for many organic synthesis reactions, establishing the first examples of chemically organized environments on Earth's surface. Only took several 100,000 years for the first complex organic polymers to begin appearing in the most chemically active pools and hydrothermal vent environments. Simple amino acids, formed through the reaction of ammonia with organic acids, start linking together into short protein-like chains that demonstrate the basic principles of biochemical polymerization. These early peptides remain far too simple to exhibit catalytic activity, but their formation proves that the fundamental chemistry of life can emerge spontaneously under appropriate conditions. Lipid-like molecules form through the combination of fatty acids with glycerol compounds, both of which arise naturally from the breakdown of more complex organic materials delivered by comets or synthesized through atmospheric chemistry. These amphiphilic molecules demonstrate a crucial property that will later become essential for cellular organization. They spontaneously arrange themselves into membrane-like structures when concentrated in aqueous solutions. The first molecular bilayers appear in tidal pools where evaporation concentrates these compounds to levels sufficient for self-organization. Carbon chemistry explores pathways toward increasing complexity through the formation of ring structures, branched chains, and other molecular architectures that will later become the foundation for sophisticated biochemical processes. The reducing environment of the early oceans prevents oxidation reactions that would quickly break down complex organic molecules, allowing fragile chemical structures to persist long enough to participate in further synthesis reactions. This chemical protection enables organic evolution to proceed through stages of increasing sophistication. Phosphorus chemistry begins establishing the foundation for energy storage and transfer systems, as phosphate ions dissolved from weathering minerals combine with organic molecules to form the first energy-rich chemical bonds. These phosphorylated compounds demonstrate the basic principles that will later evolve into the ATP energy system that powers all living processes. Though the early versions remain far too simple to serve as effective energy carriers, the chemistry proves that energy storage molecules can arise naturally from inorganic precursors under appropriate conditions. Like molecular choreographers, thermal currents and tidal mixing ensure that reactive compounds encounter each other with frequencies that optimize the chances for productive chemical interactions. The gentle circulation patterns prevent the formation of stagnant zones where reactants might become depleted, while also avoiding turbulence intense enough to disrupt the fragile molecular structures that begin forming as chemistry explores increasing complexity. This hydrodynamic balance creates ideal conditions for chemical evolution to proceed. Concentration effects in evaporating pools create the first examples of chemical selection, where some molecular species become enriched, while others remain dilute based on their individual solubility properties and thermal stabilities. Compounds that remain stable under the warm, mineral-rich conditions begin to dominate the chemical inventory. while less stable molecules quickly decompose and return their constituent atoms to the general pool of available reactants. This chemical selection process establishes the first crude mechanism for molecular evolution. Seasonal variations in hydrothermal activity create cycles of heating and cooling that drive thermal synthesis reactions during warm periods, followed by slow cooling that allows complex products to crystallize or precipitate from solution. These thermal cycles provide the energy inputs needed for endothermic synthesis reactions, while also creating the conditions necessary for product isolation and concentration. The regular cycling establishes rhythmic chemistry that operates on timescales ranging from hours to years. Sulfur chemistry contributes essential components for early biochemical systems through the formation of iron-sulfur complexes that will later become crucial cofactors in biological electron transport systems. These inorganic clusters form spontaneously in the sulfide-rich environment around hydrothermal vents, demonstrating that sophisticated metallobiochemistry can emerge through purely chemical processes. The metal-sulfur coordination compounds exhibit properties that hint at their future roles in biological catalysis. Nucleotide-like molecules begin appearing as phosphate groups combined with nitrogen bases and sugar analogues in the most chemically sophisticated pools and vent systems. These early nucleotide precursors lack the structural complexity needed for information storage and replication, but their formation demonstrates that the molecular components of genetic systems can arise naturally from inorganic starting materials. The chemistry explores the pathways that will eventually lead to the RNA world and the emergence of self-replicating molecular systems. Only took the patient stirring of ocean currents and the persistent exploration of chemical possibility space for Earth's seas to become vast laboratories where molecules could experiment with increasing complexity. The chemistry proceeds without urgency or direction, guided only by thermodynamic favorability and the statistical mechanics of molecular encounters, gradually building the chemical foundation that will eventually support the emergence of living systems through the simple expedient of allowing time for molecular evolution to explore all possible pathways toward organizational sophistication. The ocean floor takes shape as sediments settle into Earth's first underwater landscapes, building the foundations of future geology grain by grain through the patient work of gravity and chemistry. Fine particles suspended in the mineral-rich waters gradually descend through the water column, following the inexorable pull of Earth's gravitational field toward the basaltic surfaces that form the bottom of these shallow seas. Each microscopic fragment carries its own chemical history, some derived from the weathering of volcanic rocks, others precipitated directly from supersaturated solutions, and still others delivered from space as cosmic dust that has drifted down through the atmosphere. The sedimentation process operates with geological patience, accumulating layers at rates measured in millimeters per century, rather than the rapid deposition that characterizes modern river deltas or coastal environments. The slow pace allows individual particles to settle according to their size and density, creating naturally sorted deposits where the finest clays accumulate in the deepest, most quiescent waters, while coarser materials remain closer to their sources. This mechanical sorting establishes the first examples of organized sedimentary structures, proving that physical processes alone can create layered geological formations. Chemical precipitation contributes significantly to seafloor accumulation, as dissolved minerals reach saturation concentrations and crystallize directly from seawater. Calcium carbonate forms the most abundant precipitate, creating thick deposits of limestone-like material that records the chemical composition of the overlying water in crystalline form. These carbonate sediments preserve detailed information about ancient ocean chemistry, including temperature, pH, and dissolved ion concentrations that can be deciphered from their mineral structures millions of years after deposition. Scientists studying early sedimentary processes recognize that the absence of biological activity fundamentally altered the character of seafloor deposition during this epoch. Without marine organisms to create carbonate shells, produce organic matter, or bioturbate sediment layers, the early ocean floor accumulated purely inorganic deposits that followed physical and chemical laws rather than the complex biological processes that influence modern marine sedimentation. These purely chemical sediments created geological formations unlike anything that exists in today's oceans. The iron-rich chemistry of early seawater created distinctive sedimentary formations as dissolved iron combined with sulfur and silica to form mineral deposits that painted the seafloor in metallic hues. Pyrite crystals, magnetite grains, and iron silicate compounds settled into layered deposits that alternated between black, red, and golden colours depending on the local chemical conditions during deposition. These iron formations represent some of Earth's most distinctive early sedimentary rocks, preserving records of ocean chemistry from an epoch when iron concentrations exceeded modern levels by factors of thousands. Only took a few million years for these accumulating sediments to begin influencing ocean circulation patterns as seafloor topography developed through differential deposition rates in different areas. Regions receiving higher sediment inputs gradually built up into underwater hills and ridges, while areas with slower accumulation remained as deeper basins between the growing sedimentary features. This topographic development created the first complex underwater landscapes, establishing varied environments where different chemical and physical processes could operate simultaneously. Hydrothermal vents contributed specialized sediment types as mineral-rich water precipitated exotic compounds directly onto the seafloor around active vent sites. Copper sulfides, zinc sulfides, and rare metal compounds created colorful deposits that contrasted sharply with the more uniform grey sediments accumulating in other areas. These hydrothermal sediments concentrated valuable metals to degrees that will never again be achieved in Earth's geological history, creating ore deposits that preserve evidence of the unique chemistry that characterized early ocean atmosphere systems. Tidal processes reworked seafloor sediments twice daily as extreme tidal ranges alternately exposed and submerged vast areas of the shallow ocean floor. The powerful tidal currents eroded previously deposited materials and redeposited them in new configurations, creating complex patterns of erosion and accumulation that reflected the rhythmic influence of lunar gravitational forces. These tidal reworking processes prevented the formation of simple horizontal layering, instead creating cross-bedded and channelized deposits that recorded the dynamic nature of early marine environments. Compaction of accumulating sediment layers began the first stages of rock formation, as the weight of overlying deposits compressed deeper materials into increasingly dense configurations. Water expelled during compaction carried dissolved minerals upward through the sediment column, creating chemical gradients where different compounds precipitated at various depths below the sea floor. This early diagenesis established the processes that would eventually transform loose sediments into solid sedimentary rocks through the patient application of pressure and chemical alteration. Like underwater libraries, these growing sedimentary deposits began preserving detailed records of environmental conditions, chemical compositions, and physical processes that operated during Earth's early history. Each layer contained information about the ocean chemistry, atmospheric composition, and geological activity that prevailed during its formation. The sedimentary record established Earth's first comprehensive archive of environmental information, written in the language of mineral composition and depositional structure. Volcanic ash contributions to seafloor sedimentation created distinctive marker layers that could be correlated across wide areas of the ocean floor, establishing the first examples of geological time correlation. Major volcanic eruptions spread ash layers across thousands of square kilometers of seafloor, creating temporally equivalent deposits that recorded specific moments in early Earth's geological evolution. These ash layers served as time markers that allowed geologists to reconstruct the sequence of events that shaped the early planet. Cosmic dust accumulation, though quantitatively minor compared to terrestrial sediment sources, contributed exotic materials that recorded information about conditions in the early solar system. Microscopic metallic spherules, rare earth elements, and isotopic signatures from stellar nucleosynthesis settled into the growing seafloor deposits. preserving evidence of cosmic processes that influenced Earth's early development. These extraterrestrial contributions created permanent records of the bombardment history that characterized the first billion years of planetary evolution. Chemical gradients within the sediment column established different zones where various types of mineral precipitation and dissolution could occur simultaneously at different depths below the seafloor interface. Iron reduction occurred in deeper, more reducing layers, while oxidized compounds remained stable closer to the sediment-water boundary. These chemical zoning patterns created complex three-dimensional chemical systems where different types of reactions proceeded concurrently according to local conditions. Seasonal variations in sediment supply created subtle rhythmic patterns in some depositional environments as changes in rainfall, volcanic activity, or hydrothermal circulation influenced the types and quantities of materials reaching the sea floor. These cyclical patterns established some of Earth's first examples of regularly varying geological processes, creating sedimentary structures that recorded annual or longer-term environmental cycles in the growing rock record. Only took the persistent influence of gravity and the steady supply of weathering products to begin building Earth's first comprehensive geological archive, a growing library of sedimentary rocks that would eventually preserve 4 billion years of planetary history. The seafloor settles into its role as custodian of environmental memory, accumulating layer upon layer of chemical and physical information that records the changing conditions of early Earth's surface systems through the simple expedient of allowing particles to fall and minerals to crystallize in the quiet depths of the growing seas. Temperature finds its balance as water begins moderating Earth's climate for the first time, establishing the thermal equilibrium that will make complex surface chemistry possible for the next 4 billion years. The massive heat capacity of these growing ocean systems absorbs enormous quantities of thermal energy during the day and releases it slowly during the night, smoothing the extreme temperature variations that characterize the earlier, water-free planet. This oceanic thermostat operates through the simple physics of specific heat and thermal inertia, transforming Earth from a world of dramatic temperature swings into one of relatively stable thermal conditions. The global average temperature settles near 60 degrees Celsius as the planet's energy budget achieves equilibrium between incoming solar radiation, outgoing infrared emission, and the greenhouse effect of the dense atmosphere. This temperature represents a compromise between the extreme heat of the molten surface epoch and the cooler conditions that will eventually allow more complex chemistry to flourish. The thermal stability occurs not through any active control mechanism, but through the natural tendency of large water bodies to resist rapid temperature changes. Heat distribution across the planet's surface becomes more uniform as ocean currents begin establishing circulation patterns that transport thermal energy from warmer regions toward cooler areas. The shallow depth of these early seas ensures that temperature differences between surface and bottom waters remain minimal, creating well-mixed water masses that maintain consistent temperatures throughout their entire volume. This thermal homogenization eliminates the strong temperature gradients that might disrupt delicate chemical processes beginning to operate in the marine environment. Scientists studying paleoclimate recognize that these early oceans operated under greenhouse conditions that created thermal stability impossible to achieve on a planet without substantial water coverage. The combination of high atmospheric carbon dioxide concentrations and extensive ocean surface area created a powerful climate regulation system where small changes in temperature triggered feedback mechanisms that restored thermal equilibrium. This early climate system demonstrated the principles of planetary temperature regulation that continue operating today. The diurnal temperature cycle moderates significantly as water's high. Thermal capacity dampens the day-night temperature variations that created extreme thermal stress on the earlier, dry planetary surface. Ocean temperatures vary by only a few degrees between day and night, compared to the 100-degree swings that characterize the pre-oceanic surface. This thermal stability creates conditions where temperature-sensitive chemical reactions can proceed without the disruption of extreme thermal cycling. Only took several million years for regional climate variations to develop, as different ocean basins began exhibiting slightly different thermal characteristics based on their depth. circulation patterns, and proximity to active volcanic systems. Some basins maintained higher average temperatures due to enhanced hydrothermal inputs, while others cooled slightly as atmospheric circulation patterns favoured increased evaporation and heat loss. These regional variations established Earth's first climate zones, though the differences remained modest compared to modern climatic diversity. Seasonal temperature variations emerge as Earth's axial tilt begins influencing the distribution of solar heating across different latitudes and times of year. However, the moderating effects of extensive ocean coverage prevent these seasonal changes from becoming extreme, creating gentle thermal cycles that vary by only 10 to 15 degrees, rather than the dramatic seasonal contrasts that characterize continental climates. The oceanic influence ensures that seasonal changes proceed gradually and predictably. Evaporative cooling begins operating as a planetary-scale temperature regulation mechanism, with heat energy consumed during water evaporation and released during condensation in different locations. This creates a global heat engine that transports thermal energy from warm ocean surfaces to cooler atmospheric regions, establishing circulation patterns that distribute heat more evenly across the planet's surface. The evaporation-condensation cycle represents Earth's first sophisticated climate control system. Thermal stratification fails to develop in these early oceans due to their shallow depth and active mixing from tidal forces and hydrothermal circulation. The entire water column maintains relatively uniform temperatures, preventing the formation of thermoclines and ensuring that heat transfer occurs efficiently throughout the oceanic system. This thermal uniformity creates conditions where chemical processes can proceed consistently regardless of depth or location within the water masses, like a planetary blanket. The ocean system wraps Earth in thermal stability that allows delicate chemical processes to operate without the disruption of extreme temperature fluctuations. The water moderates not only daily and seasonal temperature cycles, but also the longer-term variations that might result from changes in volcanic activity or solar output. This thermal buffering creates a stable platform for the development of increasingly complex chemistry. Ice formation remains impossible under the current thermal regime, as even the polar regions maintain temperatures well above the freezing point of water. The absence of ice sheets eliminates the albedo feedback effects that will later become important components of climate regulation, but also prevents the formation of glacial systems that might disrupt the chemical processes beginning to operate in the warm oceans. The consistently liquid state of all surface water ensures uninterrupted chemical evolution. Atmospheric temperature profiles stabilize as the ocean-atmosphere system achieves thermal equilibrium through convective heat transfer and the moderating effects of water vapor. The thick atmosphere maintains warm temperatures even at high altitudes, creating thermal conditions where water remains gaseous throughout most of the atmospheric column. This thermal structure supports the vigorous water cycle that continues redistributing moisture and heat energy across the planet. Ocean-atmosphere heat exchange establishes feedback loops that maintain thermal stability, even when external forcing factors attempt to drive temperature changes. Increased solar heating enhances evaporation rates, which increases atmospheric water vapor and cloud cover, which reflects more solar radiation back to space. These negative feedback mechanisms demonstrate that Earth's early climate system already possessed self-regulating properties that resisted departures from thermal equilibrium. Volcanic heat inputs to the oceans create localized thermal anomalies that dissipate through oceanic circulation, rather than accumulating to create extreme hotspots. The water's mobility ensures that excess heat spreads across large areas, preventing the formation of thermal extremes that might sterilize chemical processes in affected regions. This thermal distribution system protects the developing chemistry from disruptive temperature spikes while maintaining overall warmth. Only took the patient thermal mass of water and the steady input of solar energy to establish Earth's first stable climate system, a planetary thermostat that will continue regulating surface temperatures throughout the next 4 billion years of geological history. The oceans settle into their role as climate moderators, absorbing excess heat when temperatures rise and releasing stored thermal energy when conditions cool. Maintaining the thermal stability that complex chemistry requires through the simple expedient of possessing enormous heat capacity and global circulation patterns that distribute energy with oceanic patience. Ancient shores meet ancient waves as the earliest coastlines experience their first meetings between land and sea, establishing the boundary conditions that will shape planetary surface processes for billions of years to come. These primordial shorelines bear no resemblance to the sandy beaches and rocky headlands that characterize modern coastlines. Instead, they form where the expanding shallow seas encounter the low volcanic ridges and basaltic plains that comprise most of Earth's early continental features. The meeting occurs gradually, without drama, as rising water levels slowly flood the lowest elevations of the volcanic terrain. The waves that approach these ancient shores carry no resemblance to the wind-driven swells that characterize modern ocean surfaces, generated primarily by tidal forces and thermal convection currents rather than atmospheric disturbances. These early waves maintain constant, gentle amplitudes rarely exceeding a few meters in height. The dense atmosphere and uniform global temperatures eliminate most of the pressure gradients that drive modern weather systems, creating ocean surfaces that remain relatively calm except during the twice-daily tidal extremes. The chemical interaction between seawater and newly exposed volcanic rock creates the first examples of marine weathering, establishing processes that will continue shaping coastlines throughout Earth's geological future. The warm, mineral-rich seawater attacks fresh basalt surfaces with chemical effectiveness that exceeds modern marine erosion by orders of magnitude. Iron, magnesium, and calcium leach from the volcanic glass at rates that visibly alter rock surfaces within decades, rather than the millennia required for similar weathering under contemporary conditions. Scientists studying coastal geomorphology recognized that these early shoreline processes operated under fundamentally different conditions than those governing modern coastal evolution. The absence of significant wave energy from wind-generated storms eliminated most mechanical erosion, while the extreme chemical reactivity of the warm, mineral-rich seawater accelerated chemical weathering far beyond modern rates. The result created coastlines that evolved primarily through chemical dissolution, rather than the mechanical abrasion that shapes contemporary shores. Tidal action in these coastal zones creates erosional and depositional features that dwarf any modern tidal landforms. The extreme tidal ranges of 20 to 30 meters carve massive tidal channels through the soft volcanic sediments and create intertidal zones that extend inland for dozens of kilometers. These vast tidal flats experience complete submersion and exposure twice each day, creating unique environments where marine and terrestrial chemistry can interact under alternating conditions. Only took a few thousand years for these tidal processes to begin carving complex drainage networks through the coastal volcanic terrain, establishing the first organized channel systems on Earth's surface. The rushing water of extreme incoming tides follows topographic lows and gradually deepens them through hydraulic erosion, while the retreating flows deposit sediments in patterns that record the direction and strength of tidal currents. These early drainage systems create templates for water flow that will guide coastal evolution long after tidal ranges moderate to more modest levels. The thermal effects of these coastal interactions create unique temperature gradients, where the warm seawater encounters slightly cooler terrestrial rocks. These thermal boundaries establish zones where different types of chemical weathering proceed simultaneously, with temperature-dependent reactions occurring at different rates depending on local thermal conditions. The result creates chemically complex coastal zones where multiple weathering processes operate concurrently. Salt crystallization begins occurring in the upper intertidal zones where evaporation concentrates seawater beyond the solubility limits of dissolved minerals. These early salt deposits create the first evaporate formations on Earth's surface, preserving records of ancient seawater chemistry in crystalline form. The salt crystals grow during low tide periods when exposed tidal flats experience direct atmospheric evaporation, then redissolve during subsequent tidal flooding cycles. Sediment transport along these ancient coastlines operates primarily through tidal currents, rather than the longshore drift that characterizes modern coastal sediment movement. The twice-daily reversal of tidal flow creates complex patterns of erosion and deposition where sediments move back and forth along the shoreline without developing consistent directional transport. This creates coastal morphologies that reflect the oscillatory nature of tidal processes rather than unidirectional wave action. Like geological laboratories, these coastal zones establish the first environments where terrestrial and marine chemistry can interact under controlled conditions. The regular alternation between aquatic and atmospheric exposure creates unique chemical gradients, where reactions impossible in purely terrestrial or purely marine environments can proceed through hybrid pathways. These boundary conditions explore new possibilities for chemical complexity that require both aquatic and atmospheric components. Rockpool formation begins occurring in coastal areas, where tidal recession leaves isolated bodies of seawater trapped in depressions carved from the volcanic substrate. These early tide pools maintain elevated temperatures and develop concentrated mineral solutions as evaporation removes pure water and leaves dissolved salts behind. The pools become natural evaporation chambers where seawater chemistry can be concentrated to levels that permit exotic mineral precipitation. Wave refraction around headlands and coastal promontories creates the first examples of focused erosional energy, as wavefronts concentrate their limited energy on specific portions of the coastline. While the waves remain modest by modern standards, their consistent application to particular coastal features begins the process of differential erosion that will eventually carve complex coastal geometries. The refraction patterns establish the first examples of organized wave-coast interactions. Coastal vegetation remains absent from these early shorelines, eliminating the biological influences that characterize modern coastal environments. Without root systems to stabilize sediments or organic matter to modify soil chemistry, the coastal processes operate through purely physical and chemical mechanisms. This creates coastlines that evolve according to thermodynamic and hydrodynamic principles, without the complications introduced by biological activity. Chemical zoning develops in coastal sediments as different minerals precipitate at characteristic distances from the high tide line, creating organized patterns of mineral distribution that reflect the chemical gradients between marine and terrestrial environments. Iron oxides concentrate in the most frequently flooded areas, while silicate minerals accumulate in zones that experience less frequent seawater contact. These chemical patterns establish the first examples of environmentally controlled mineral distributions. Only took the patient interaction of water and stone to begin carving Earth's first coastlines, establishing the fundamental processes that will continue shaping the boundaries between land and sea throughout the next 4 billion years of geological evolution. The shores develop slowly but persistently as tidal forces and chemical weathering gradually modify the volcanic terrain that forms these early continental margins, creating complex boundary zones where terrestrial and marine processes can interact and explore new possibilities for geological and chemical evolution through the simple expedient of bringing seawater into contact with volcanic rock under the rhythmic influence of tidal cycles. Life's precursors gather silently in protected tidal pools, assembling without urgency or haste in the sheltered waters where chemistry begins its first tentative experiments with self-organization. These shallow basins, carved by tidal action into the volcanic coastlines and warmed by geothermal heat from below, provide ideal conditions for the concentration and interaction of organic compounds that have been accumulating in Earth's oceans for millions of years. The pools serve as natural laboratories where simple molecules can explore increasingly complex arrangements without the disruptive turbulence of the open seas or the dilution effects that prevent productive chemical interactions in larger water bodies. The molecular inventory within these tidal sanctuaries includes amino acids synthesized through atmospheric chemistry, fatty acids delivered by cometry impacts, and nucleotide precursors formed through hydrothermal reactions. These building blocks of future biological systems drift in solution at concentrations thousands of times higher than those found in modern oceans. creating conditions where chance encounters between reactive molecules can lead to productive chemical combinations. The warm water accelerates reaction rates while the protected environment prevents the immediate breakdown of complex products. Evaporation cycles in these pools create natural concentration mechanisms as water loss during low tide increases the density of dissolved organic compounds to levels approaching those found in modern living cells. When incoming tides dilute these concentrated solutions, the sudden change in ionic strength can trigger precipitation reactions that create the first organized molecular assemblies. These evaporation-dilution cycles establish rhythmic chemical processes that operate in synchrony with tidal periods, creating the first examples of environmentally driven molecular organization. Scientists studying prebiotic chemistry recognize that tidal pools provided the ideal combination of concentration, protection, and chemical diversity needed for complex organic synthesis to proceed beyond the random molecular interactions that characterize open ocean chemistry. The pool served as reaction vessels where reactant concentrations could build to productive levels, while maintaining the thermal and chemical stability needed for complex molecular assembly processes to reach completion without interruption. Clay minerals deposited in these pools by tidal action provide catalytic surfaces that accelerate organic polymerization reactions and help organize simple molecules into more complex arrangements. The layered structure of clay particles creates organized environments where amino acids can align in configurations that favor peptide bond formation, while the mineral surfaces provide nucleation sites where lipid molecules can begin assembling into membrane-like structures. These mineral catalysts operate without requiring the sophisticated enzyme systems that drive modern biochemistry. Only took several 100,000 years for the first self-assembling molecular structures to begin appearing in the most chemically active tidal pools. Amphiphilic molecules, possessing both water-loving and water-repelling components, spontaneously organize into bilayer membranes that create the first cell-like compartments in Earth's history. These primitive vesicles lack the sophisticated transport systems and internal organization of modern cells, but they demonstrate the fundamental principle that certain types of molecules naturally organize themselves into boundary structures. Protein-like polymers form as amino acids linked together in chains that begin exhibiting rudimentary catalytic properties. While these early peptides remain far too simple to rival the efficiency of modern enzymes, some demonstrate the ability to accelerate specific chemical reactions by factors of 10 to 100. This represents the first emergence of catalytic activity from purely chemical systems, proving that molecular machines can arise naturally from the random polymerization of organic building blocks under appropriate conditions. RNA-like molecules begin appearing as nucleotide analogues combine into short chains that can store limited amounts of chemical information. These primitive information storage molecules lack the stability and replication accuracy of modern RNA, but their formation demonstrates that the basic principles of molecular information storage can emerge spontaneously from inorganic chemistry. The early RNA analogues explore the fundamental relationship between molecular structure and information content. Chemical selection processes operate in these pools as some molecular combinations prove more stable than others under the prevailing temperature and chemical conditions. Compounds that resist thermal breakdown or chemical degradation gradually become more abundant, while less stable molecules quickly decompose and return their constituent atoms to the general reactant pool. This natural selection among molecules establishes the first crude mechanisms for molecular evolution, based on differential survival rather than biological reproduction. Like molecular nurseries, these protected pools provide safe havens where fragile chemical structures can persist long enough to participate in further synthesis reactions that might lead to increased complexity. The combination of protection from disruptive forces, concentration of reactants, and catalytic mineral surfaces creates ideal conditions for chemical evolution to explore pathways towards self-organization that would be impossible in less favorable environments. Energy gradients within these pools, created by temperature differences between sun-warmed surfaces and cooler depths, provide the thermodynamic driving forces needed for endothermic synthesis reactions that build complex molecules from simple precursors. The thermal gradients create natural energy sources that can power chemical work without requiring the sophisticated energy coupling systems that characterize living organisms. These energy flows establish the first examples of organized energy utilization in chemical systems. Autocatalytic reaction networks begin developing in some pools as certain molecular products catalyze their own formation, creating positive feedback loops that can amplify small initial concentrations into significant molecular populations. These self-reinforcing chemical cycles represent the first examples of molecular systems that can grow and reproduce their own chemical components, establishing the basic principles that will later evolve into biological reproduction and metabolism. Chemical oscillations appear in pools where competing reaction pathways create cyclical changes in molecular concentrations over timescales, ranging from hours to days. These oscillating chemical systems demonstrate that purely inorganic processes can create regularly varying conditions that might eventually coordinate more complex chemical processes. The oscillations establish some of Earth's first examples of chemical rhythms that operate independently of external environmental cycles. Compartmentalization begins occurring as membrane-forming molecules create isolated chemical environments within larger pool systems. These early compartments allowed different chemical processes to proceed simultaneously without interference, creating specialized microenvironments where particular types of molecular assembly can proceed optimally. The compartmentalization establishes the first examples of chemical division of labor in prebiotic systems. Only took the patient concentration of molecules and the gentle rhythm of tidal cycles to create these protected laboratories where chemistry could begin its first experiments with the organizational principles that will eventually lead to living systems. The tidal pools continue their quiet work of nurturing molecular complexity, providing stable environments where simple compounds can explore increasingly sophisticated arrangements through the persistent application of thermodynamic principles and the concentrating effects of evaporation cycles that operate with tidal regularity across thousands of coastal sites. The blue planet completes itself as Earth settles into its new identity as a water world, patient and ready for the eons ahead. Across the volcanic archipelagos and shallow continental shelves, the great work of ocean formation reaches its first stable equilibrium. Water covers nearly 70% of the planet's surface, distributed among thousands of shallow seas, temporary lakes, and interconnected waterways that collectively hold roughly the same volume of liquid that will characterize Earth's oceans for the next 4 billion years. The planet has discovered its capacity for holding seas, transforming from a molten ball of rock into something unprecedented in the inner solar system, a world where liquid water can exist in vast quantities under stable conditions. The global water cycle operates with newfound sophistication as evaporation, condensation, and precipitation establish regular patterns of moisture distribution that will continue operating throughout Earth's future history. Atmospheric water vapor rises from the warm ocean surfaces, condenses in the cooling upper atmosphere, and returns as rainfall that feeds the very seas that provided the original moisture. This circular system creates Earth's first self-sustaining planetary process, a mechanism that operates independently of external inputs while maintaining the conditions necessary for its own continuation. Ocean chemistry achieves its initial equilibrium as the balance between mineral inputs from weathering rocks and losses through precipitation and evaporation stabilizes at levels that can persist for geological timescales. The seas contain dissolved sodium, calcium, magnesium, and iron in concentrations that reflect the volcanic composition of the early continental masses and the chemical composition of the dense atmosphere that surrounds the planet. This chemical foundation will evolve slowly over billions of years, but the basic patterns of oceanic mineral distribution become established during this epoch. Scientists studying comparative planetology recognize that Earth's successful transition to a water world represents a remarkable achievement in planetary evolution, requiring precise balances between solar distance, atmospheric composition, and planetary mass that allow liquid water to exist on the surface for billions of years. The planet occupies the habitable zone around its star with sufficient precision to maintain surface temperatures within the narrow range where water remains liquid under prevailing atmospheric pressures. The temperature regime stabilizes in a configuration that will persist until biological processes begin modifying atmospheric composition billions of years in the future. Global average temperatures settle near 50 degrees Celsius, warm enough to support vigorous chemical processes but cool enough to prevent the wholesale evaporation of the ocean system. This thermal balance creates conditions where complex chemistry can proceed without the disruption of extreme temperature variations or the stagnation of excessive cooling. Only took several 100 million years for these oceanic systems to demonstrate their capacity for supporting increasingly complex chemical processes that hint at the biological transformations still far in the future. The seas serve as vast reaction vessels where simple molecules can explore pathways toward organization and complexity under conditions that favor synthesis over decomposition. The chemical experiments proceeding in tidal pools and hydrothermal vents established the foundation for processes that will eventually lead to the emergence of living systems. Atmospheric composition achieves a temporary equilibrium as volcanic outgassing balances with chemical absorption into the ocean systems and mineral precipitation processes. Carbon dioxide concentrations remain hundreds of times higher than modern levels, creating greenhouse conditions that maintain warm global temperatures despite the young sun's reduced luminosity. Water vapor contributes additional greenhouse effects while also driving the atmospheric circulation patterns that distribute heat and moisture across the planet's surface. Geological processes begin operating through the interaction of water with solid rock, establishing the weathering and erosion cycles that will continue shaping planetary surfaces throughout Earth's future evolution. Chemical weathering of volcanic rocks releases minerals into solution, while mechanical erosion by waves and tidal currents begins carving the complex topography that will eventually create diverse coastal and marine environments. These geological processes establish the first connections between solid Earth systems and surface water chemistry. The Moon's gravitational influence creates tidal patterns that will gradually evolve as orbital dynamics slowly increase the Earth-Moon distance over geological time. The extreme tidal ranges of this early epoch begin the process of dissipating rotational energy through friction with the shallow sea floor, simultaneously slowing Earth's rotation and forcing the Moon into higher orbits. This tidal evolution establishes the long-term trajectory that will eventually create the familiar 24-hour day and more modest tidal ranges. Like a planetary circulatory system, ocean currents begin establishing circulation patterns that transport heat, dissolved chemicals, and suspended materials across global distances. The shallow depth and uniform temperature of these early seas create relatively simple circulation patterns driven primarily by tidal forces and atmospheric pressure variations, rather than the complex density-driven currents that characterize modern deep oceans. These early circulation systems established the first global transport networks for chemical and thermal exchange. Seasonal variations begin influencing oceanic processes as Earth's axial tilt creates modest differences in solar heating between different latitudes and times of year. The oceanic thermal mass moderates these seasonal effects, creating gentle climatic rhythms rather than the dramatic seasonal contrast that characterize continental environments. These seasonal patterns establish the first examples of predictable long-term environmental cycles that operate on timescales longer than daily or tidal rhythms. Chemical gradients develop between different oceanic regions, as local conditions create variations in mineral composition, temperature, and chemical reaction rates. Some areas become enriched in iron due to enhanced hydrothermal inputs, while others develop higher concentrations of carbonate minerals through increased rates of chemical precipitation. These chemical variations create the first examples of oceanic provinces with distinct chemical characteristics and specialized chemical processes. Sedimentary processes establish the first comprehensive geological archive, as materials eroded from volcanic terrains and precipitated from seawater begin accumulating in organized layers on the ocean floor. These sedimentary deposits preserve records of atmospheric composition, ocean chemistry, and environmental conditions that will remain legible for billions of years. The sedimentary archive establishes Earth's first permanent memory system for recording planetary environmental history. Hydrothermal circulation systems create connections between surface ocean chemistry and deep crustal processes, establishing chemical exchange mechanisms that will continue operating throughout planetary history. These circulation systems transport surface materials into the planet's interior, while bringing deep crustal chemistry to the surface, creating feedback loops between internal and external planetary processes. The hydrothermal systems established the first examples of planetary-scale chemical cycling. Only took the patient accumulation of water and the gradual cooling of planetary surface temperatures for Earth to complete its transformation from a molten, sterile ball of rock into a blue marble capable of supporting the complex chemistry that will eventually lead to living systems. The planet settles into its oceanic identity with liquid satisfaction, having discovered through millions of years of experimentation that water and rock can coexist in stable configurations that create ideal conditions for chemical complexity to flourish and evolve toward ever greater degrees of molecular sophistication and organizational beauty. The blue planet turns slowly in space, its surface gleaming with the reflected light of shallow seas that stretch toward horizons shrouded in water vapor. Earth has become something new under the sun, a world where chemistry can dream of life. The oceans breathe quietly now, their surfaces rising and falling with the gentle rhythm of tides that have found their eternal pace. Steam no longer rises in towering columns from the cooling waters. The copper sky has softened to deeper greys as atmospheric circulation settles into patterns that will persist for millions of centuries. Earth's fever has broken. The planet floats in space wrapped in its new blue skin, patient as stone, fluid as time itself. In the deepest parts of these shallow seas, currents move like slow thoughts through warm water. Minerals dissolve and precipitate in cycles measured not in seasons but in millennia. Iron-rich water carries the rusty dreams of cooling magma chambers toward shores that will forget their volcanic birth. Chemistry continues its quiet experiments in the protected pools and hydrothermal gardens, building complexity molecule by molecule with the unhurried persistence that only geological time permits. The moon pulls at these waters with gravitational gentleness, no longer the close companion that once raised 30-meter tides. Its face watches over the blue marble of Earth as thermal equilibrium settles across the planetary surface. Day becomes night becomes day, in rhythm with the planet's slowing rotation. 20-hour cycles stretch gradually toward the familiar 24-hour days that will someday mark human time. Volcanic islands sleep beneath their blankets of warm seawater, their fires banked but not extinguished. Heat flows upward through basalt foundations, keeping the overlying waters at temperatures where chemical evolution can proceed without haste or urgency. The planet has learned patience from its own thermal mass, discovered that lasting change requires time measured in eons rather than moments. Somewhere in the quiet tidal pools, amino acids link hands in chains that will not break easily. Lipids organize themselves into membranes that isolate small volumes of specialized chemistry from the larger oceanic laboratory. RNA-like molecules begin their first tentative experiments with storing information in molecular form. These are not yet alive in any sense that will later be recognizable, but they represent chemistry's growing sophistication, its gradual discovery of organization and purpose. The planet sleeps fitfully, still cooling but no longer restless. Its surface has found the stable configuration that will endure for billions of years: oceans and islands, chemistry and stone, heat and water in equilibrium. Earth has become itself at last, a blue oasis in the cosmic darkness where complexity can flourish, and time moves with the unhurried rhythm of tides In the deepest silence of these primordial seas, the future waits with molecular patience. Stars wheel overhead in patterns that will change as slowly as the chemical experiments proceeding in Earth's tidal laboratories. The planet turns, the oceans breathe, and chemistry dreams its slow dreams toward awakening. Only took 4 billion years of patient geological time to reach this moment of oceanic completion. Only took the cooling of stone and the gathering of water. Only took the endless rainfall and the patient tides. Only took the gentle stirring of currents and the quiet accumulation of possibility. Earth sleeps now as a water world, blue and patient under ancient starlight, ready for whatever chemistry might dream in the protected pools where molecules learn to dance with increasing complexity. The planet has found its identity in the marriage of fire and water, stone and sea. The oceans rest. The chemistry waits. Time flows like current through eternity. Sleep well, Blue Earth, sleep well.